Yeah, so hello everyone. It's great to be here. And today I'm going to tell you about Apache TVM. So to give you a sense on what Apache TVM is, it is end-to-end uh, machine learning framework for deploying deep learning models onto various of hardware platforms. And to see like where we are at, if you look at the current deep learning landscape, there are different frameworks and engines. There's compiler, and then finally there are also like a kernel libraries out there. So the main question that a lot of that a lot of people have is right now a lot of the approaches that people take are using hand optimized libraries, and TVM really sits in this spectrum of being able to try to generate automatic kernel libraries that help us to deploy machine learning model to various kind of hardware platforms. So to give a sense of how TVM is different from the current machine learning systems, most of the current learning system tries to build machine learning solutions to enable machine learning. On the other hand, uh, there's also this question of we need to spend a lot of effort building those systems. So can we actually use machine learning to optimize the system themselves? So that I can spend less effort, or the TVM community can spend less effort to go and optimize the system. The answer is yes, and we will build what we call learning-based learning system that not only build system that enables machine learning, but also use machine learning to optimize those systems in return. So in particular, I'm going to tell you a bit about TVM. And the task that we are looking at when building TVMs, we want to be able to deploy machine learning models onto various kind of hardware backends, including your data center CPU, GPU, Raspberry Pis, all those specialized accelerators. The main gap of this deployment is actually huge. So to give you a sense of how does existing deep learning frameworks solve this problem, most of the existing frameworks represent the high-level computation of those frameworks in what we call high-level data flow graphs. And each of the color nodes correspond to a primitive tensor operator, such as like convolution 3D or convolution 2D. And in each of the color operators, actually, there have to be someone to go and implement those libraries. For example, in the case of NVIDIA, there's a library called CUDN that go and implement those operations. The limitation of this approach is, of course, it will cost human resources. And in a lot of cases, you will also want to be able to combine a few nodes together into a new what we call fused operation, which gives you potential speed up actually on the execution. However, the question now is we have to implement a blue node in the new library, and it's happened exactly to us a few years ago. And well, what we did then is we call NVIDIA, and then after a year they add that back. As you can see, it's very time consuming and human engineering resources consuming. And if you multiply that by the amount of hardware devices you want to support, it's a very engineering intensive process. So that's why we want to try to build a more automated solution. The idea is we want to be able to replace the human-based effort by a bit more automation to build a machine learning program optimizer that automatically generates the high-level data flow graphs and optimize those programs and directly generate code that can be deployed onto new hardware and new workloads. So specifically for this, in order to do that, we will try to describe the high-level grain node in what we call tensor expression language, and then we'll try to build a space of possible program optimizations based on specification, and we can generate low-level variants from that. For example, to give a sense, you can directly write a for loop that runs this matrix multiplication. If you have written like CPU-based optimization before, you might know that you want to be able to tile the loop a bit so that it enjoys better cache locality. Or if you want to map to specialized accelerators that you like, you might want to map some of the instructions to the accelerator instruction that these programs provide. So in a nutshell, we want to be able to combine billions of possible optimization choices and search over that space in order for us to get a better program. So to formalize this, we can use SLE to denote the search space. And our goal is to be able to generate an optimized configuration for the optimizer that gives you a program. And our objectives, you want to minimize that execution time. So there are a few ways we can do that. For example, one of the ways to do that is you can what we try called black box auto tuning. You just try out different configurations, send it to the target hardware, and try it again and again until you find a good solution. The problem of this approach is, of course, it's very time consuming. You need to run a lot of experiments before you, hey, it works or it does not work. Another approach we can do is, we can learn from typical database community by defining what we call a cost model that estimates the cost of a program and use that to drive the search. The problem of this approach is that usually it's very hard to design a very accurate and reliable cost model for each of kind of hardware we're interested in. So instead, we take what we call machine learning based approach. The idea is that we want to be able to use the high level configuration to generate a low level AST and extract statistical features from a program, and then use a machine learning based predictor to predict the cost of the running program. The advantage of this approach is, of course, we can also use like a neural network based approach that use a tree GRU model to encode the input program. The advantage of this approach is actually, tree-based model gives you pretty good predictive accuracy. It is also kind of task invariant in a sense that you can transfer the model across multiple program domains because the AST is shared. By using this machine learning based cost model approach, we can actually get pretty decent performance. For example, here's a benchmark on a single layer of running convolution 2D operator on a Titan X GPU. If you directly use a black box approach, it can give you pretty decent performance. But if you use the machine learning based optimization, you can find that it will give you better performance than the CUDA baseline in this particular case. The reason is not because machines are better than human. It's simply because machines can specialize in a particular case to find a specific code that optimizes for this particular operator. Another important perspective of this is that not only we can build a cost model for a single search purposes, we can reuse the cost model to predict the cost of a new task. So as the compiler starts to collect more data, it becomes smarter, and it will learns to predict the cost more accurately and find better programs faster. To give you a sense of what kind of this transfer learning approach can bring you, this is the original curve, and if you use transfer learning for this particular case, that can actually give you a pretty good performance boost. On average, it's not as good as this one, but on average, you can get a 3x to 10x speed up over a non-transfer case. So in a nutshell, by using a learning-based approach, actually we can scale the automatic program optimization to a pretty large scale and further speed up program optimization using transfer learning. So far, I've talked about this kind of machine learning component of this. TVM is actually an end-to-end deep learning compiler that contains a larger system component with machine learning as its core. So I will talk a bit more about how do we define a search space in here. For example, for a tensor expression, to recall, we want to define a search space that maps from high-level expression to the low-level valid hardware programs. And in here, one of the most important things is how can we define the search space? For CPU-based programs, actually, we can reuse a lot of existing primitives by existing frameworks like Halide or Loopy to be able to do loop transformations, to make use of cache locality, and do better vectorization. Things become more interesting as we start to look at other kind of hardware like GPUs or emerging new accelerators. For GPUs, one of the important things we want to be able to make use of the shared memory and do thread cooperation effectively across the GPU thread to cooperate to fetch data onto the GPU shared memory. Things becoming mostly interesting when you start to think about TPU-like accelerators. These accelerators are both special in terms of their compute primitives and the memory subsystem they expose. So let's talk about compute primitives. So traditionally, when you write programs, you can just write a scalar program. You just write for loops to compute each element of a target. It's very flexible. And as you start to use the vector instructions like AVX512 or ARM's Neo instruction, we will need to be able to write programs that make use of the vector instruction that imposes some kind of constraints on your program. If you look at the new accelerators, or the instruction like tensor core instruction in NVIDIA's GPU, things becoming even more complicated. We can write a single instruction that performs matrix vector product or matrix product. These instructions are usually high dimensional, and it's really hard to enumerate all the possible tensor instructions out there. So our challenge is how can we build a generic system for all the potential emerging tensor instructions. In order to do that, what we do is, besides using a declarative language for computer specification, we also use the same language to specify the hardware interface specification. In this case, we describe the matrix vector product of an 8x8 matrix vector instruction. And what we do is we will employ what we call tensorialization process that will try to mix and match the computer specification to the hardware interface specification in order to lower the code to make use of the hardware instructions out there. And I don't have time to talk about the hardware memory scope, but in another to combine this from prior works, as well as bringing new primitives from GPUs and other accelerators to enable new acceleration. So far I've talked about how does the TVM works in both the machine learning optimizer component as well as the code search space component. Let's talk about what we can do by bringing everything together. So here's the benchmark from end-to-end inference on NVIDIA Telltale GPU. This benchmark is a bit old. If you go to the TVM blog post, there are a lot of interesting latest results as well. So both TensorFlow and Apache MXNet are backed by CUDM library. And if you run TVM, you can find that you can get better performance. And there are a few highlights in here. For example, if you look at the left side, it's a model on ResNet 18, and we can get pretty competitive performance on those kind of standard models. What's most exciting takeaway, though, is that we look at far right, this is a model called Deep Q Learning model, and we get a 3x better performance than the standard deep learning framework. What is the reason from here? The reason is that we will be able to use the we want to be able to in this case, because the library vendors are heavily optimized for standard benchmark like ResNet 18 because they are paid to do so. On the other hand, on those emerging workloads like a deep Q learning model, or if you are thinking about any model that runs on your local on your local company, a lot of cases people are developing customized models, and those libraries are not well optimized for those customized models. So what's happening here is that TVM-based solution can give us automatic optimization on those emerging models as well, so that you can see this 3x performance boost on a lot of cases. We have seen a lot of successful stories of the community deployment case of Apache TVM. Similarly, another interesting thing is we can use the same solution and get portable performance across hardware platforms. In this case, we can run TVM on both ARM CPU and ARM GPU and get better performance than the native solutions on those platforms. And finally, we can also build solutions that optimizes for latest hardware. This is an example on NVIDIA's Tensor Core. Again, we can find that in this case, this is speed up over the existing solution. So we can find that we can get 1.5x better on transformer-related workloads on this case. And again, this is the takeaway on how can we build automatic optimization that gives you better performance on emerging workloads. So far we have talked about what is TVM and what benefit it can bring you. Let me switch gear to talk a bit about where the TVM community is going in the last year actually. So there are a few important directions we are looking into. The first direction is we are building a unified runtime for deploying heterogeneous devices. In this case, one of the important things in a lot of deployment cases, we are starting to see a need to be able to deploy on multiple devices, including things like CUDAs, NPU, or some external runtimes like TensorRT. What we build so far is we will introduce a unified interface for all these device-specific runtimes as what we call a device module, and we can plug them back into the TVM runtime and exposing them into a single binary file. So by having this unified runtime, we will be able to generate programs that runs on multiple devices, including CPU, GPU, and NPU, very effectively using a single interface. It also gives you some free benefit, like TVM have a have language bindings on all those major languages, including Python, Java, Go. We even have a WebAssembly interface that allows you to directly call from a web browser. And you can directly get those free API bindings by making use of the unified runtime. You can also get things like automatic RPC support that allows you to upload your programs onto a remote devices and do remote benchmarking so that you can say, automatically generate an optimized program on your Android devices without worrying about, how to directly access. The second thing that we are actively going on is we want to build unified intermediate representation that allows us to unify both high level and low level optimization together into what we call a common module. And in order to do, by doing that, it allows us to mix and match different levels of representations in a single IR module, and allows us to do some cross representation optimization. Finally, we are also looking into what we call first-class Python support, which means that we want to be able to use Python as a first-class citizen to be able to represent the intermediate representation and write as the intermediate representation. So developers will be able to directly write their IR programs in Python and manipulate them using Python API. This allows us to accelerate innovation because ML-based compilation is still a very young field, and we can mix and match programs in both Python and C++ if you want. And you can also shift to C++ when your Python prototype is product ready, so that it gives you a path from research to production. Finally, we also want to be able to rethink the low-level tensor IR to introduce things like automatic scheduling and better tensorization support to support more heterogeneous tensor specialized hardware. Another thing that we're actively looking at is be able to, as an open source project, to be able to interpolate with other existing machine learning compiler infrastructure. In particular, we are working on bringing in models from both TensorFlow and PyTorch, and be able to also generate code that contains external functions and make use of customized packaging and customized code generation. So besides the both unification in terms of runtime and IR, one of the final things we're looking into is trying to bring in full stack automation. In this case, our currently the AutoTVM tries to automate the optimized operator generation stage, and we want to be able to enlarge that support to use AutoTVM across all the layers, including the high-level optimization as well as the hardware-specific optimizations. So so far I've told you a bit about TVM, and I would like to spend the last minute to talk about community perspective. And as you know, the Apache TVM is an Apache project, and this means that it really enables independent governance that allows multiple organizations to even competitors to collaborate on the project. And so far, TVM is very active, and we developed the project on the Apache way, which means that every developing events are open. You can follow our mail list and Discourse forum on that. And there's an open governance model followed by the Apache Software Foundation guideline. It has also been widely adopted by a lot of the industrial partners, including academia and industry, such as Amazon, Intel, Facebook, ARM, Qualcomm, to name a few. And it has already powers some of the industrial applications. One of the notable examples is that Alexa's wake word actually is optimized by TVM's optimization. We are also holding an annual data conference. This year is virtual. So if you go to tvmconf.org, you will find more information there. With that, I would like to conclude my talk, and I will be more than happy to take any questions. Okay, thank you. Yeah, any questions? Yeah, so I forgot to include the link to the TVM conference. So if you are interested, I will post it on the chat, and please go and check it out. There's also links to last 2 years conference, including video recordings, and you can check out the existing applications from different industry partners, different industry organizations that are contributing to the community. Yes, so one of the questions, what is the focus, right? So first of all, TVM itself is is natively built in C++. So we really want to enable productization on that perspective. And it's also cross language in a sense that right now you can access TVM from languages like when you deploy TVM, you can deploy it into bindings like uh, C++, Python, JavaScript, Go, and any other languages. But Python is indeed one of the first class citizens we want to support, because we see a lot of use cases where people want to directly write machine learning program in Python and directly call compilation and deployment from there. Things that TVM is developing the core to be cross-language. So for example, there's also a recent movement to bring Rust as a first-class citizen, because there are some interest in security and deployment community on doing that. Yep. Yeah, if you have any additional questions, you are more than welcome to post to the chat or directly speak out. I believe that's also possible. Yes, the question is about, is there any use cases where it is being used in production? The answer is definitely yes. So if you go to TVM conference 2019, you can find that you can find talks from different companies, like for example, Alexa's Wake Word is one example that is already TVM already powers the AWS SageMaker Neo services. It also drives some of the Facebook as click-through product pipeline. And you can find quite a few use cases actually nowadays using TVM in production on various use cases in both the cloud setting as well as the embedded setting. And we will also love to hear a lot more use cases if you are interested in using TVM in your product. Yeah. Okay, so let me know if there's any. Okay, so there's the additional question about, is there easy hello world or Docker container type demo to get started? TVM. So if you go to tvm.apache.org, there is documents about how do you get started. Unfortunately, right now there's there is a Docker container, but on the other hand, because the Docker container is kind of a convenient generator, so you can try to go and try to get quick started on the tutorials. Because there's a dependency on a VM, so you kind of need to build from source. But there are also third-party binaries that you can go and check out and install from a third party. On the other hand, the community usually maintains a fully Apache compatible source release that you can go and build for your local use cases. You're welcome. Yeah, so I think I would just stick around for a few more minutes, since officially the session still wouldn't and until 9:40. If you have questions, feel free to type in. And yeah, thank you, Felix. Okay, thank you again for coming to talk, and I'm going to leave for now, but enjoy the rest of. Thanks, Felix, for hosting. Yeah.